Okay, now double click on Fluent. Now right click on geometry. We aren't designing any sort of a structure over here because if we are working on 3D, either yes, you need to design or you can directly import a existing model. So now I'll click on import, browse, and then I'll just check the CAD model where I have kept. Now I select the CAD model and then you will find a green color tick mark. That means the design has been selected. Now right click on geometry again, click on design modeler. Now wait for it to load. Instead of space claim, now we are working on existing CAD model, right? We need to create an environment for it. So this is the design modeler workbench. Now you cannot see the object right now. You need to click on generate. Over here you can find the option called generate. Now just click on it. If you click on generate, wait for it. It will take some time. Now you see the missile over here. The thing is, we will be performing external airflow dynamics upon this missile, basically to find out how the turbulence or the vortices have been created. Now, the main intention of this analysis is because you can see this fins, right? The missile fin. It is having a increment of 10 degrees. Okay, it is actually rotate. The missile is actually rotates. It rotates when it is moving. You need the control surfaces to act accordingly, right? So it is at 10 degrees. So we will check out how the overall characteristics of it would be like. Now next thing is that when I am working on any sort of simulation, I will first click on Z-axis. If I click on Z-axis, I'll be making sure that it is in XY plane. Like Y is over here, X is like this. You can see, right? Now, according to ANSYS default setting, the airflow comes from left and goes away from the right. Now that's why, see, the thing is, wherever the nose cone is facing, that should be my inlet. But here the rocket is, the missile is facing downwards. So what I'm going to do right now is change the orientation of the missile. To change the orientation, you need to click on create on the top left corner. And there's an option called as body transformation. In the body transformation, choose rotate. All you need to do is just click on the design, just single left click and apply over here on the bodies. And next thing is, how do you want to rotate it? So which axis? I'll choose the axis XY plane. With respect to XY plane, apply. It's 45 degree. I don't want 45 degree. I want 90 degree. Now you see, right, how the missile's orientation has changed to 90 degrees. It is now facing the x-axis. Now if you want to make sure this is the final design, the orientation, just click on generate again. It is done. The missile is facing this side, right? Now next thing is you need to create an environment. So basically we call it as fluid domain. We apply very big box for naming the fluid domain. The same thing will be applied over here. To apply the fluid domain, I'll click on tools, enclosure, and then just randomly click generate. Just click generate. You will find a box like this, right? So this is the fluid domain basically. So fluid domain is nothing but the environment. Now center click on the mouse button, you can move it like this. Now I want the fluid domain to be quite more bigger. To make sure it is big, you can see the dimensions of the fluid domain through with respect to positive x-axis, positive y-axis, positive z-axis, and negative xyz axis. Everything is 1 meter. It's a 1 meter cube. Instead of 1 meter, I'll give it as 5. I press everything as 5. Generate. Zoom out. Now you can see a bigger fluid domain, right? The reason why I apply bigger fluid domain because you will be able to track the shock waves, the stagnation point, any sort of vortices inclination or environmental reaction. These things can be spotted very quickly and better. So that's why I want a bigger environment. Now next thing is I will have to create Boolean condition. So you people do know, right? When I was working on the 2D simulations, we used to delete the object in between when the overall fluid domain was present. The same thing will be done over here. Now, next thing is we need to apply Boolean condition because there is a theory from Navier-Stokes equation. The theory states that to make sure and to ensure proper aerodynamical characteristics of any object, if you want to notify and find out each and every behavior with respect to turbulence, with respect to vortices, with respect to stagnation point or shock wave, or let it be anything, if you want to track each and every detailed data of it, you need to consider the whole environment must be treating as a continuous medium. If you treat your environment as a continuous medium, then you need to delete the object because let's take it simple, okay? In the real-time environment, the object will be solid and the air is cavity, na? Air is cavity. But now in the ANSYS software, it cannot comprehend real-time nature. So if it doesn't comprehend the real-time nature, it will make the opposite. The whole environment will be treated as a continuous medium, like a solid piece, and the object we need to delete it so that it will be a cavity mold. So I hope all of you know how sand casting is done, right? Like sand is the solid and you put a mold pattern and you remove it and there will be a cavity shaped in the sand mold with respect to object design. We need to create something like that. Now to do that, you just have an observation. The missile looks gray color. I mean, it's a solid piece, right? Now I'll make it a cavity. To make it cavity, it is pretty simple. Click on create, boolean. Instead of unite, I'll keep it as subtract. I am subtracting the missile from the environment. So I select the environment and click on target body. And I will select the part over here, the body over here, so that missile is selected. Because inside I cannot select the missile like this. So I'll select the body over here. If I zoom in, yellow color is selected. I'll apply over here. Simple, right? Now, just have a look. It is visible. If I click on generate, the boolean will be operated. You can see the shock symbol over here. If it is shock symbol, you are yet to click on generate. If it is green tick mark, the operation is done. Now operation is not yet done. Just see, I'll click on generate, observe the design. It became transparent, right? Like a glass. That means it is a cavity right now. If this is a cavity, the whole environment will be treated as a continuous medium. This gives utmost precision for any sort of simulation. Now, next thing is we will have to name it because we used to give inlet, outlet or far field conditions, right, in the 2D. But now over here, we'll be naming the inlet, outlet, everything in this section itself. To do that, it is pretty simple. Just click on the whole box, name it as far field. To name it as far field, right click on it, name selection. Over here on the bottom left corner, I will name it as far field, FARFIELD. That means it's a complete open airspace environment. And click on generate. Now you can see far field and a tick mark over here. Next is I need to name the missile inside. To name the missile inside, I cannot do exactly like that. And most of all, the missile is not over there. It is deleted. It is absent. But I can see a cavity now. The faces have been still over there. So I will choose face control, like selecting the faces. Box is selecting the cube. This is face control. Now to select something on the inside, I'll click on selection mode. You can see the top left now, selection mode. Box select. Make a big rectangle like this covering the whole missile. Do one thing, okay? Make sure it is a big rectangle. Don't do something like this, like only some will be selected. I don't want something like that. I want the whole missile to be selected. Then right click on it and name it. I'll name it as missile. Simple. And generate. So both far field and missile have been named as of now. So that's the only step for the design modeler. I'll just close it. Ansys will automatically save it for you. Then right click on mesh, click on edit. Now, next thing is, if you get in the meshing right now, I'll just go to mesh. All I need to do is click on element size. It is 918 mm. Any number, okay. It will be some random number. For me, it is 918 mm. For you, it will be 1000. For someone, it will be 500. So whatever it is, keep it to the nearest digit. I'll assume it is 900. 900 divided by 2 is 450. Now click on generate. You are just trying to decrease the cell size. The lesser the cell size, the more accuracy. I will decrease it a bit more. I'll assume it is 400. 400 divided by 2 is 200. I can actually give it 225, but still, I'll just make sure it is simple. So I guess 200 mm is enough. It will take a lot of time. So this is actually enough. You can decrease a bit more. You don't need to work on inflation, boundary layer meshing, or any other sophisticated methods to increase the accuracy, because you have already been working on the cavitation method or Boolean method. If you do that, then these things doesn't matter at all. So that's why we make sure it is small enough. This is enough in cavitation method. Click on update. Make sure at the bottom right corner you will get a message telling it is successful. Then directly close it. Just close it. Right click on setup. Click on edit. Now you need to give your laptop's or PC specification. I'll give it as 4 solver processor and start away. Now next thing is, center click on the mouse button. You can actually rotate your design like this. I don't like this reflections. It's kind of making it look a bit weird. So I will hide it. I'll click on the first option here, disable graphics reflection. It is gone. Then I'll select this one, graphics shadow. The shadow you can see, right? The static shadow. I'll click on that. Then third, the grid panel. It's gone. Now then click on display. You need to click on display, general, unselect wall far field, display and close. If you do that, you can see the missile over here. See, the meshing is still, the meshing is good, but at the joint section, it is irregular. That means it's very simple for me. I just need to decrease the element size. It will be proper. For example, at the nose cone, it is all done good, right? But at this section, we need to concentrate a bit more, and eventually it will happen. So not a problem. All I need to do is just decrease the cell size. But remember, I can decrease it. I can increase the accuracy. But solving time will be a bit more. Right now we are solving at just 100 iterations, 500 iterations. It will hardly take 5 to 10 minutes. Or it's only for simulation purpose so that you guys can understand like what's going on. And then when you work on the actual projects, I will be making you guys work for 5,000 iterations, 10,000 iterations. Then click on pressure based, go to models, Now turn on the energy equation. Now we need to turn on the energy equation over here because let's say the incoming airflow is making a contact on this surface, the fins, and the overall environmental effect on it. So there will be energy imbalance due to surface friction, air friction, turbulence, all those things. So make sure you click energy equation to find out the imbalance. Then viscosity. So the missile which we are working on right now is this supersonic missile which travels at Mach 2.5 speed. So for that, I'll be choosing K epsilon. It is supersonic, na? For supersonic, transonic, subsonic speed, you go for K epsilon. For hypersonic or something like high pressurized base flow, you go for K omega. Now this is K epsilon. Apply viscous heating. At the bottom, you can find viscous heating, right? So due to continuous airflow upon it, there will be a heating effect acting on it. So that's why make sure you apply all those things, then press OK. Finally, you go to materials, double click on air. Now the thing is that over here, keep it as ideal gas because let it be a flow upon the missile due to sudden temperature or pressure changes or velocity disturbance. We cannot predict the air manually. So if we set it as ideal gas, it will obey all the different types of gas laws. So eventually it will autonomously adjust its parameters with respect to any sudden changes. So we don't need to worry about it. So ideal gas based simulations is preferred in any type of simulations. Then click on create, close. Now next thing is boundary conditions. One more thing, if you want to make the missile rotate in a sense the missile rotates and the flow around it will behave accordingly. Now, so you need to click on cell zone condition, then far field, edit. So here you can apply mesh motion, you can select at which angle it is rotating, at which axis it is the magnitude, and what is the rotational velocity. All those things can be added. But now I won't be doing that. Okay, I won't be doing that because we don't need it. I'll be teaching that later. Now next, I'll click on boundary conditions, wall far field. Now it's a pressure far field condition. Click on pressure far field. Now this missile is gonna be at sea level condition. It is literally shot from a naval vessel, right? So I'll just keep it as 101325 Pascal. That's the standard atmospheric pressure condition. Next is Mach number. So for the Mach number, I'll give 2.5. Now next is the XYZ coordinates. So there is flow coming from x-axis. Now just assume like this. There's a flow coming from x-axis, right? The drag acts in x-axis and the lift acts in y-axis. So that's the thing that's gonna matter to me. Z-axis, there is no flow coming from z-axis. So let's ignore it. Now, x is cos theta, y is sin theta. Theta is the angle of attack. Now cos of 0 is 1, already answers as given. Sin of 0 is 0, already given. Now I will choose angle of attack of 5 degrees. So cos of 5 degrees 0.992, sine of 5 degrees 0.087. That's it. That's how you choose the angle of attack. Then temperature, it will go up to 600 Kelvin. It's actually 650 Kelvin. The temperature around the surroundings will be around 180 to 300 degrees Celsius. Apply and close. Then go to methods, Make sure everything is second order so that you can complete the simulation faster and better. Initialization, initialize. Okay, now the thing is at the bottom you will get a message telling that warning convergence tolerance has not reached. So you don't need to give a damn about it because we do get this warning many times, but we also have achieved convergence even if we get the warning. So that's not a problem, okay? Because we are working on a cavitation method. We are not working on an existing body. We are working on cavitation method or Boolean method. So that's the advantageous thing what we got right now. So we don't need to worry about it. Then run calculation. Number of iterations, just 100 is actually enough. I'll click on 100. So let it tend to calculate. Now, once the calculation has been complete, you can see this lines going right. It represents xyz velocity, energy k epsilon. So what is this xyz velocity? Now, once it makes a contact on the body surface due to friction, there will be turbulences, deflection, all those things happen. Now, with respect to all three different plane conditions, the velocity, the energy will tend to decrease. So you can see it is all decreasing down due to friction. Next, energy K epsilon. Even the turbulence will decrease with respect to friction and any sort of disturbance. Now, what did we do? We got a converged solution, right? So the answers told we'll be having some warning over here. We won't get convergence. But here we have achieved the convergence. So basically, what is convergence in the answers? It is nothing but, let me tell you, once the flow makes a contact on the surface, it goes out, it tends to topple. Okay, to be circulating at some point it stops. So convergence in answers is nothing but the point which has least number of errors. In a very simple way, the fluid's property like pressure, velocity, temperature will be completely zero. That is called as convergence. And we have got the converged solution. Just 100 iterations. You saw the difference, right? Cavitation method. So you got convergence way more faster. If you go for existing body design with sophisticated meshing techniques, you require at least 3000 iterations. So that's the difference. We aim for like getting things done faster. That's how the industries work. Now go to results, double click on graphics, double click on contour. Do not close this tool, okay? Do not close it. Now pressure and static pressure. There are many types. You can view pressure, density, velocity, temperature, turbulence, many. In pressure, you have multiple. Static pressure, pressure coefficient, dynamic pressure, total pressure. Even in velocity, there are many types. First, I'll go with pressure and static pressure. I will apply on the missile display. Now for 10 degrees angle of attack, this is where it is affecting. At the bottom, the pressure is high, na? You can see the color gradient. So now have a look. Maximum pressure is 1014. Pressure is acting more over here. At the top, the pressure is less. Why? Because like the thing is, it depends on the angle of attack. The shock is converging more at the bottom on the rather than the top. When the shock wave is being formed, right, at the bottom it will be compressed due to angle of attack. At the top, the flow separation tends to be more bigger. Even at the fence, it's exposing over here only. This is for 10 degrees angle of attack. Now now let's say if the pressure is acting too high, now let's say on this fin control system the pressure is acting high. then I can opt for any sort of structural support and assistance. Then we do static structural analysis to find out. We call it as aeroelasticity. I will teach that later. Okay. For time being, this is enough. Now next is temperature. Overall temperature contour. You can find the values here. 1585 Kelvin. It increases because of the speed and the pressure acting on it. Even skin friction. Next, wherever the flow separation is over there, see, one thing is that you're still not able to see the 2D perspective now. That's why I'll click on new surface, plane. I'll put new plane, XY plane. This is the view I want to see. Create and close. Now unselect missile, select only plane, display. Now this is the temperature contour, 2D. I'll go with pressure. This is the shock wave. Where angle of attack is high, the shock is converged over there. At the top, it is diverged. This is the flow separation, velocity. This is the stagnation point. But this will cause drag. But thrust is being produced now, so it doesn't matter. Mach number. This is the shock wave. Now next is, we will perform animation on it. Click on path lines. Select missile only. Draw mesh. Display and close. Velocity. I want only 50. Continuous and pulse. Now you can see the animation perspective where you can figure out where the vortices, the turbulence have been forming up. So you can see the turbulence over here. So this is stagnation point. So in, so in this method, you can try figuring out where the drag is more, where the vortices is more, and you can try eliminating it by changing the design. So here I have given a wedge airfoil. The airfoil what you're seeing right now is a bi-wedge airfoil. Next is click on stop. If you click on stop now, like you can visualize it without moving. So at the fins, there is very minimal drag. It's a very good design. At the back end, don't worry about the turbulence. There will be rocket thrust that will be produced now. Okay.